So now we are ready for structure refinement. So if you go to your ins file and you want to view it, you can see clearly that it's changed a little bit. Right now you can easily see your new comments right here, and we will talk about those comments maybe later on. But the beginning of the file, it's absolutely the same what was for structure solution, but for structure refinement we get structure refinement program comments. And here so you can see the atom information, and it's telling you the label of atom, type of atom, it's this number, then it gives you x, y and z coordinate of each atom, occupancy, and thermal parameter of the atom. FVAR means free variable, and first free variable, it's always you will have scale factor here all the time. So right now it's unrefined, all our thermal parameters are the same. It's clearly indications that we didn't refine anything. So well, let's do refinement. To do refinement we're using the Excel program. So we type Excel and name of file, which means Diels. Pressing enter, something happens. Let's see it with Ctrl O. And we can clearly see how the refinement goes. Now we can see the values of WR2 factor begin with 61, and each cycle you can see it's going down and stabilizing about 35.59. so it's very good indication that refinement go in right direction. And right now our R factor, which is main R factor, around 10.76%, which is very good for isotropic refinement. When we go to anisotropic refinement, it will go more down. What else we need to look for? It's maximum shifts. They should be around 0, but you can see we begin with 16 and we're still going down. So later on we will still push them to 0. And for now you also need to look on highest peak. So you shouldn't have very high peak. If you have like high peak around 4, it means you're missing some atom or something else happened. Deepest hole also should be very small, or otherwise it will correspond to some effects on your crystal. But right now it's pretty standard. It's not such a big. It's about 1 electron peak. Maximum peak, so we'll see where it's located on the next step. So let's see the results of our refinement, and again we've seen them in XP, so I'm typing XP and name of file Diels. Going to XP, beginning with fmol. Select all the atom. Let's see approach. So let's see, you can again logging. I hate logging, and it's not why it's logging, but right now you can clearly see our structure with the new peaks of residual electron density already, and majority of them, it's obvious that they correspond to the hydrogen, but still let's see where our highest peak is located. Let's do info. And how I told you, info will give you information about the atoms. Nothing what you need to look, it's on the E equa or U equa, which is correspond to your thermal parameters for your atoms, and they should be approximately the same for all atoms. Not Q-peaks, but all atoms, they should be approximately the same, and you can see they approximately around 20 for all the atoms. It corresponds that you probably don't have any disorder, which is quite good. Okay, now we have Q1 is the highest atom, it's about 1 electron per cubic angstrom, so let's see where it's located. To do so, we wanna just to see our structure plus this highest peak. How to do that? You do it with fmol again. So fmol it's collect atoms, yes, and you start with O1. It's first atom in your list, and you type 2 Q1. So you cut it at Q1. It won't collect any atoms below Q1. If you do that and do proj, you can see. So Q1. I hate when my structure lagging. I'm sorry. Let me try to do it again. It never lags when I doing structure solution without video recording. But hopefully now you can see it's clearly correspond to one of the hydrogens. So it doesn't correspond to the any other additional atoms. But we cannot name any hydrogen atoms until we go to anisotropic refinement, and that will be our next step. So let's go out from here. So what I want to do is kill $qpix. Do not save the qpix before new cycle of refinement. Save only atoms. And again I'm typing file deals. Say quit. Okay, and to do the refinement, what we're gonna do, maybe let's do, let's do maybe one more cycle of, no, let's do actually anisotropic refinement. Yeah, I think we're ready for it. So we go to F4, F4 to the ins file, with, to modify it, and you see the free line between plan and VGHT. Put their word anis, which correspond to anisotropic refinement. Say escape. It's asking you, do you want to save your change, what you did change in the file? You say yes. Now repeat Excel. So you type Excel deals. Press enter. Something happens again, and you can see our factor went down from 35 till 31. Our 1 become 9%. Our shift also very close to 0, but we still have high peak, about 1 electron per cubic angstrom around C3, distance 1.1 angstrom. So it's very probably correspond to the hydrogen position. So the next step, we will need to see, we would need to see what actually happens and find all the hydrogen. So I went again to XP, fmol. Let's do fmol less $q. So it collects all atom except the qpix, and see if our structure change or not. Well, it'll look like our structure stay intact, so it's very good for us. Also very good comment for you to notice. Let me find the good orientation of the molecule. Pairs, which allow you to see the structure. Oh my goodness gracious, it really takes a long time. Usually it takes very quick, but it allows you to see your model in ball and stick. So sometimes I'll probably will use it for you to show how it happens. I actually might know why it's actually happening. Let me try. Okay. Okay, maybe now it will work better. Let me try pairs again. No, it's still slow. Okay, but pairs, it's a really nice comment which allows you to see your model in ball and sticks. Usually it happens fast if you don't do any video recording on the screen. Okay, let's go escape from that, and let's do info to see is anything happens with the atoms, and look like no, they stay intact. No funny thermal parameters, so you're fine. So the next thing what you want to find is you want to find your hydrogens. Well, how you do that? Pretty much you do what you first need to do is to change atomic radius for the cubics, because as default it's correspond to the carbon atomic radius, but hydrogen of course have much small. So what you do, you type arad $q, dollar means all in the structure, yes, 0.2, press enter, and this command doesn't work without another fmol. So if you do fmol, do approach. Oh, I know what I forgot to do. I forgot to collect all the cubics at first. So arad $q 0.2 0.2 again. So let me repeat fmol. If you do that right now, you can clearly see how the atoms are separated. So cubics all separated, but you still have several bad cubics which do not correspond to the hydrogens. So what you can do with them? Well, one of the things what you can do is to get rid out of them. How you can get rid out of them? All the same way how we separate our good cubics from bad cubics. So you do info $q, which may correspond, give me information about all cubics, and if you look, all our cubics until Q17 Q17 have values very close to 0.8, 0.9 or even 1 electron per cubic angstrom. Everything below it have around 0.4 electrons. So they probably bad cubics. So what I want to do is kill Q17 to Q20. And what we should see if we type approach, we should see only hydrogens, yes. So now let's name the hydrogens. We name hydrogens the same way as we name carbon. At least it's fast way to name them. So name Q question H question, and name Q double question H double question. So approach, and you see now you have all your hydrogens. So now this way, oh, I hate it, I'm very sorry. Let's try to do it again. Okay, so this way we find all our hydrogens. So we actually find them from residual peaks of electron density. Yes, another way is to put hydrogens on calculated positions, but we will do it maybe when we will discuss organometallic structure. Here I can easily find my hydrogens, so I can actually refine their position and their thermal parameters very easily. So let's go escape from it and let's file our data file. So file Diels. So we wrote everything, and now we need to do refinement. If you go to ins file, let's see how it's changed. Oh, it's changed quite a bit. You can see for carbon and oxygen atoms we have more parameters. It corresponds to the ellipsoidal parameters for the anisotropic refinement, and all our hydrogens here, they're in isotropy, and they will be always in isotropy. So almost done. Okay, now we do in Excel. Excel deals, and if we see our R factor went down, the way WR2 went to 14%, and our R1 went to 5%, so it's very good. And our high peak evaporated, so it's 0.5 electron per cubic angstrom, so it's very small peak. So we finally found our final model. So the next step would be still refine some parameters of this model and prepare the C file for publication.